So we take those DNA samples and we collect them together, we gold coat them, and we embed them into a metallic disc that you can't quite see on the camera, but it has a convex shape to it. We take that disc, which is actually quite a bit smaller than this, and we put it onto what amounts to something like a very sophisticated shotgun shell. But instead of having the pellets in the shotgun, we actually have this disc in there, and the only thing behind it is the charge itself. If we were to fire this system the way we are going to organize it, it blows this disc out at an extremely high velocity. It's what's called an explosively formed shaped charge. The military does this kind of stuff all the time, right? So all the DNA is in this disc, and it's going to be super accelerated by something that's akin to the shotgun shell, except it won't be quite as big as this. But going through the atmosphere at extremely high speed, it gets white hot. What can we do about that? Well, one of the things we could do is let's move it where there's no atmosphere. So the next approach is let's get something that we can shoot up the high atmosphere. So in order to do that, let's make ourselves this cool arrow. Now this arrow is actually full size to what we would shoot. And this tube here really amounts to a .50 caliber gun barrel. But where this differs from most .50 caliber guns is that it has a smooth bore inside. So it's an unrifled .50 caliber barrel. This smaller version of a projectile goes inside here. Normally we would think about it being shot, it would come to the end of the barrel and come out. We're going to change that approach a little bit. We'll talk to that in a minute. So let me look at it and say, great. So this is in here, and I'm going to instead push this through the atmosphere at high velocity, all the while protecting this. So I'm going to take a cannon that we're going to take a look at in a minute how we're going to do this. I'm going to take a cannon and shoot this. Right? But it's going to get red hot too, and what's going to keep it from just wiggling around in space? That's why we have fins. We don't want to rifle our cannon either. One of the reasons we don't want to do that, it uses up all the energy. So we don't spin stabilize, we fin stabilize this projectile. We better have some kind of point on this to penetrate that atmosphere without getting too hot. That's what we have here. And again, this is full size to what we'd actually use. This goes on the end of this .50 caliber barrel. So when it's going up through the atmosphere, this hits the atmosphere first, absorbs the heat, and on we go. The fins keep it stabilized. Well, when we get up there, we have to know when to shoot off our .50 caliber, which looks more like this size here. All right. We need to know when to fire this off to start, remember this is oversized, to start this kind of system down the barrel. Well, we have a way to do that. On this end, we have a little bit different system. All of this, by the way, goes out at one time. So in here, we have some electronics. We know roughly how fast this .50 caliber arrow is going to be moving. And we know roughly how much it's going to slow down from atmospheric friction, which means we know about how long it's going to take to get to 200,000 feet, 300,000 feet, at which point we don't have a problem heating this disk any longer because there's virtually no atmosphere. As soon as the larger cannon fires this system off to push it up through the atmosphere, the timer in here starts. This round, the 50 caliber round, the propulsion, will fire somewhere between 200,000 and 300,000 feet. Now, do we care really whether it's 200,000 feet or 300,000 feet? Not really. Anywhere in there is fine because there's still no atmosphere at that altitude. We would like this whole system to fire before it gets to 325,000 feet, 350,000 feet. That's sort of where the edge of space is defined. And we don't want to put any extra objects in space and have to fight with some officialdom about, oh, well, you're putting something up in the space corridor. We don't want to do that. The only thing we want to be going through there is this tiny little disc, this little pointed thing that'll be made out of this as it forms explosively. So this timer goes on to here, and some other elements go on to there. All right, so a smaller version of this, with a disc on it is moving down this barrel. Well, normally you'd think, well, let's let it come out, and then we're going to fire it, and this disc will form its shape, and off it'll go at high speed. There's a problem with that. If we come out of the barrel, we don't know that this thing may start to try to tumble. Right? And we don't know exactly how we're going to fire it. So if this comes out and we fire outside the barrel, rather than going in the same direction as the 50 caliber, it could maybe roll a little bit and fire. We don't want that. We want everything to stay straight in line with what our shot is, which is exactly vertical from the Earth. We take a different strategy. What we do is, as this gets up close to the end of the barrel, we have contacts, electrical contacts on this, right, that say, oh, I'm almost out of the barrel. And then it fires. So now it's maintaining its orientation, and we don't have to figure out how we're going to orient it while it's traveling at high speed and it's already out of here. This thing just splits. So it's like a clamshell. It goes like that. Pretty simple to do. We don't need it to be penetrating the atmosphere anymore. There is none. So it goes like this. Our charge moves down the line here, reaches this general area, makes contact. Embedded in this region, we have batteries, fast discharge batteries. Right? They release their energy, fire this round, right, electrically, and off this goes. So that's all good. But we have to reach a certain velocity. So we have some speed that we got from the cannon that shoots this off, and then from the 50 caliber round going down here, we have more velocity that we picked up, and then when the shaped charge goes, we have even more velocity. So we're adding all these velocities together to reach the kind of velocity that will actually allow the disk that contains the DNA to escape the influence of the Earth. All right. But we have to get this thing moving along to make the altitude. So let's take and put ourselves together a long cannon. How long? 40 feet. Right? Now this, compared to what we talked about earlier, where we had the very deep hole, like 600 feet, and a rocket that shot a rocket and all these sorts of things, we've bypassed that. Now for the cannon, we have to have a certain size bore in it. All right. Now, the velocity of this coming out of our big cannon that shoots this into the upper atmosphere, its bore size is determined by several things. All right. The mass of what it's trying to shoot to altitude, and the area that has to be pushed. So the bore size. This is about 3.3 inches. We need the 3.3 inch rather than some other smaller diameter because we have to get enough area. All right, remember the area of a circle is pi r squared. So the more we open this, the better, and it gives us an increased area quickly. Now we have pressure. So we have this detonation going behind it, which is really a conflagration going on behind it, pushing this out. All right? Pressure is force per unit area. We hear it say like pounds per square inch. Well, if you increase the number of square inches, then you end up with pounds. If you have pounds of force, then it's pushing pounds of material here, right? And it's accelerating it out quickly. So we have a certain mass. If we know what the force is, there's another equation that says that force is equal to mass times acceleration. So when we work all this arithmetic out, which is not really high-level arithmetic, when we work all this out, this works just fine. We have someone who's dealt with this for the military for years and years and years, and that's how we end up with a 3.3 inch bore. All right, so with simple equations, we can see that we're going to get a push on this that's proportional to what the pressure profile is in the cannon barrel times the area that we're dealing with and any kind of drags we get when this thing is trying to go out. So we just can't willy-nilly put something together, and we can't just simply take this system and put it down into our cannon barrel because, look at, the stuff's going to just blow by. The gases that we use to propel us, they're just going to go by. So what can we do about that? Well, that's handled all the time in systems, military mortars and all the rest of that sort of thing. They use, and we're going to show an example here, they use a sabot. Now, this is a 3-part sabot. And I'm going to put that 3-part sabot around this 50 caliber system like this. Now, what happens? When we are in this tube, it's closed up. Right? And it's designed so that this surface actually expands against the inside of the cannon tube. The way this works is, this is where the pressure comes, and it's pushing up this way. This is actually down when we start out. This is down in the combustible material. This is actually down in the fuel that shoots this thing. But it's done all the time. Mortars and cannon systems do that all the time. This can take the heat, and it's a very short period of time. This is where it seals and pushes out. Well, we have something that's important to us here, and that is, we don't want to carry this into space. This adds a lot of weight. And what's the value of having this point here if then we have this big blunt section here? Well, the way these work is, this is compressed inside the cannon as it goes, but this is formed here with scoops. So as soon as it hits the air, what it does is it peels off like this. So it's coming out, first hits the air as it comes out of the barrel, and each one of these starts lifting off like this and blows away. So now we're rid of those. Again, I want to point out all this stuff is actually to full scale. We've really studied this, and we've come up with some ways to make the shooting inexpensive, easy to deploy. So this is coming out. That peels off. This goes up to 200, 300,000 feet. Our little timer says, ooh, wow, time to shoot the 50 caliber round. The 50 caliber round goes off. And as it approaches the end of the barrel, there are contacts that then cause it to fire. All right, it takes the little cap that's on the end of that shotgun sort of round, comes up here, bang, goes off, forms a charges thing, and off it goes. By the time you add all the velocities together, you're so fast you're going to escape the influence of the Earth's gravity. And we've calculated different orbits and stuff that we can put this into. But there's a lot of force associated with that. And this can have an effect on the DNA. Well, we've looked at the problem of how do you keep DNA in space for hundreds of thousands of years and allow for the fact that cosmic rays may go through it. The solution that we've taken there is the same solution to any breaking of the molecules that we might get from this explosively formed process, because there's a lot of force on it. There are hundreds of thousands of Gs. There's hundreds of thousands of times the force of gravity pushing against us. If we were on there, we'd just end up being a puddle of fluid. But we anticipate there's going to be some breakage. How do we get around that problem? Again, we used the same solution that we used to determine how we get by the reality that cosmic rays over hundreds of thousands of years are going to sever some of these DNA molecules. So here I have 5 sets of DNA. I'm just going to look at one of the DNA molecules. We have several of them in the whole chromosomal structure. But I'm going to take one of those, and let's say we started it out in full length. So this just keeps going, and this piece adds this piece, and so forth. If these are the base pair sizes, in other words, the code on the DNA just goes along like this. It just stretches along the DNA, and it has this helix structure. Well, what happens if this breaks up? How do we know, or even how does advanced civilization even know how this stuff goes back together? Well, what we do is we send more than one. So let's say we send 2. So these are the same, but they're broken up. Their links are broken up very much different than these links. That's okay, because if we take a piece of this, it overlaps 2 pieces of the other one differently. So if we had one of these other ones, like this, and we have a piece of its material, then we can just see how these guys go together because we match the overlaps. So we look at these codes. And we've done some calculations that show if we send up 10 sets of DNA, the chances of not being able to reassemble the DNA, even if we break in tens of thousands of places, the chances of not being able to put it back together are far less than 1 in a million. Now, we can just look at it and say, well, each DNA needs to be, 1 million base pairs long, and maybe we can do something with that, but that's helpful. But what you really need to do is be able to make this overlap mapping down there. So we can take tens of thousands of breaks in the DNA as we do this explosively charged projectile function. We can still figure out how to put it back together. We're working on refining those calculations to really nail down what's the probability. Well, let's say the probability of your DNA not being reassembled 250,000 years from now is 1 in a million, right, or 1 in 10 million. Right? You have that probability of getting killed walking across the street for a month, particularly if you're in the city. Right? So, can you ever have a situation that you won't be able to have your DNA reassembled exactly the way it should be? Yeah. Yep. But it's pretty small. So that's how we do it. So in summary, let's remember, all right, rather than using some very expensive, large rocket-propelled system, what we've done is we've used a cannon, and it's about a 40-foot long cannon, and we'll we'll talk about that. It's about 40 foot long. We float it out to sea, and it rotates it at sea, and we shoot it straight up. So we got the international waters where we don't get a bunch of hassle, and we shoot it up. We're not going through the atmosphere with that flechette. We're not going through the atmosphere into space with this. Doing it this way, all right, cannon shooting basically a gun barrel, shooting a round with a shaped charge in it. Inexpensive and totally unique. So it's just one of the super cool things that we get to play with in this project. And we'd like to welcome you aboard.